In this video, we're going to take a look at stationary points and second order derivatives. So up to now, everything we've done has involved the first order derivative only. So what we mean by that is if we have a very basic equation, let's say we've got y equals x squared. Okay, so this is just a very basic example here. If we differentiate this, we get dy by dx. So we get dy by dx. And this is what we call the first order derivative, or just simply the first derivative. And in this case, it will simply give us 2x. Okay. Now, if I differentiate this again, so if I differentiate dy by dx here with respect to x, what I get then is the second derivative. And the way we express this, the notation we use, is given as follows. Okay. That's how we express the second derivative. And in this case, we just differentiate here 2x with respect to x again, and that would just simply give me 2. Okay. Now, if we're using function notation, so if I do this using function notation here, we'd have f of x. So f of x is equal to x squared. Remember, the first derivative is f prime of x, so f prime of x, which is equal to 2x again. And now if we differentiate here again, we'd get f prime prime of x, okay, like so. And again, that would simply just give me 2 for the second derivative. Now, why do we want to use the second derivative? Well, the reason we use the second derivative is because it comes into use with looking at stationary points. So I guess the question here is now, what is a stationary point? Well, when we differentiate, okay, and we find the first derivative, this is important, okay, because this allows us to work out the value of the gradient for a given x value, okay. Now, to find a stationary point, this is where the gradient is equal to 0. So if we just think about a really basic example here, if I just sketch, say, I don't know, y equals x squared plus 2, okay? And we get a quadratic that looks like that, okay? It's going to cut through at 2 here on the y-axis. That's my y-axis. This is my x-axis here. Now, where the gradient is equal to 0, notice this would just give me a straight line. Okay, let's get a straight line here. Okay, so it's neither increasing or decreasing. Okay, so what we've got here is, so this is when dy by dx is equal to 0, or alternatively, f prime of x is equal to 0. So if I've got the equation here, let's just say y equals x squared plus 2. Okay. Well, if I differentiate this here, we'd get dy by dx is equal to 2x. This constant here would disappear, so we just simply get left with 2x. And what we'd do now is we'd set dy by dx equal to 0. So therefore, we'd have 2x is equal to 0. And therefore, in that case, x will be equal to 0. Okay. But if x is equal to 0, we can then find the y coordinate by substituting x into this equation here. So y is equal to 0 squared plus 2, giving me 2 there. Okay, so we know the stationary point occurs at 0, 2 there. Okay, so that stationary point there is 0, 2. Now, in the case of a very basic example like that, we don't really need the second derivative because we expect for a quadratic like this here, a positive quadratic, that this would just be a minimum point. And we can easily work out the stationary point here, okay? But if we have something like, say, a cubic, where we might have a maximum and a minimum, the reason the second order derivative is really important is because it allows us to work out the nature. So what we mean by that is whether it's a maximum point or a minimum point, or we might even possibly have a point of inflection, okay? So how do we determine this? Well, what we do is we differentiate, get our first derivative, and we set that equal to 0, okay? We then differentiate again, and that would give us the second derivative. And from the second derivative here, we have 3 conditions. So we have when the second derivative is greater than 0. So when the second derivative here is greater than 0, and what this tells us is that our stationary point is a minimum point. Okay, so that's a minimum. If we have that the second derivative is less than 0, the second derivative here is less than 0, then this is a maximum. This is a maximum. And finally, run out of room a little bit. If the second derivative here is equal to 0, then this could potentially be a point of inflection. Now we have to be careful here. Doesn't necessarily mean it will be a point of inflection. We have to do a bit more work to determine that. Okay, but point of inflection I can't spell, so point of inflection, possibly when the second derivative is equal to 0. Okay, so we'll say possibly there. Okay. Now the reason this is a possibly is because basically we have to be very, very careful. And what we need to check is whether the second derivative changes sign either side of our stationary point. Okay, so like I said, it's worth mentioning that just because the second derivative is equal to 0, it doesn't necessarily mean the stationary point will be a point of inflection. Okay, but we'll come across that in more detail when we take a look at exam revision for differentiation. We're not going to look at that too much in this video, but let's take a look now at some kind of practice questions based on stationary points and the second derivative. So I've got 3 parts here. All we're going to do is find the second derivative. So notice this is again the notation we're using here for the second derivative. So I've got y, we differentiate once and differentiate again. Now we've actually already seen this example here, probably not the best example to start with, but if y is equal to x squared, well, we differentiate once, that would give me dy by dx. So dy by dx, that would simply be 2x. So we get 2x there. And now if we differentiate again, we're going to get the second derivative here. We just differentiate dy by dx again with respect to x, and it would just simply give me 2 there. Okay. So for the first one, we simply get 2. For this next one here, we have to be slightly careful about how we express this. So I've got y equals 2 over x cubed. What I want to do is write that in index notation. So this is the same as 2x to the minus 3. Okay. So again, what we do now is we start by finding the first derivative here. So dy by dx. So that's going to be 2 times minus 3, which is minus 6. So I get minus 6x. Then we subtract 1 from the power, so that's to the minus 4. Okay. There's no point in changing how we write this again because we need to find the second derivative. So again, let's just use this notation here. So if we do this over here again, for the second derivative now, again, we just differentiate dy by dx here with respect to x. So minus 6 times minus 4, so that's going to give me positive 24 now, so just be careful there. We get positive 24x, and then again, we subtract 1 from the power, so I get 24x to the minus 5. And if you really wanted, you could write it in this kind of form here. So that's going to give me 24 over x to the 5 there. Okay, you could write it like that if you want. It's not necessary, but if you would like to, that's how we could express it as well. And then for this last one here, c, well, again, I'm just finding the second derivative. So all we do is we go term by term. Okay, so first we need to find the first derivative. So dy by dx. Term by term here, x cubed, that would give me 3x squared. 3x squared here, if we differentiate that with respect to x, that would give me 6x. We get plus 6x. Minus x would be minus 1. And this plus 1 here, remember when we differentiate a constant, that's equal to 0. Okay, so that's the first derivative. Now we just simply differentiate again here to get the second derivative. If I differentiate again here, 3x squared, once we differentiate that, well, we've already seen that here, we get 6x, so that's 6x there. If I now differentiate 6x with respect to x, that will give me plus 6. And once I differentiate minus 1 here, well, that's a constant, so once you differentiate that, that will become 0. Okay, and that's what we get for part C there. So if I just highlight the solutions clearly, let's just do it in a different pen colour. This was for part A, this was for part B, and this was for part C there. Okay, so there we have it. So that's the solution to A, B, and C. Moving on to 2 more examples here. This time we're using function notation. So what I want to do then is find the second derivative. So in function notation, that's going to be f prime prime of x. Now, to start with here, what we need to do is get rid of these brackets. So what I'm going to do is just expand. So 4x on the outside, 4x times x, that gives me 4x squared. And then we've got 4x times minus 5 giving me minus 20x. Okay, so that's minus 20x. Now, what we actually want here is the second derivative. So what I'm going to do is just differentiate once. That gives me f prime of x. So all we do here is we go term by term. 4x squared, that will give me 8x. We get 8x there. And minus 20x, once we differentiate that with respect to x, that just simply gives me minus 20. We get 8x minus 20. So now what we need to do here is differentiate one more time. So that's going to give me f prime prime of x. So that's f prime prime. Not quite very nice. F prime prime of x. And here what we do now is we just differentiate f prime of x, again, term by term. So 8x with respect to x, that will give me 8. And minus 20 here, well, that's a constant, so once we differentiate that, that's equal to 0. So here we get f prime prime of x is equal to 8. So that's the solution to part A. Just note that there. Let's have a look at part B now. So the first thing I need to do here is, again, get rid of these brackets in the numerator. So if I expand this here, x times x gives me x squared. X times 4 would give me 4x, but then don't forget we do minus 3 times x. So that's minus 3x. So 4x minus 3x will give me plus x. We get plus x there. And then finally, minus 3 times 4 gives me minus 12. So that's my numerator once we expand those double brackets. And this is all over our denominator still of x squared. So what I want to do here now is go through term by term in the numerator and cancel with my denominator. So I've got x squared over x squared. Well, that's just going to be 1. We get 1 there. I've then got x over x squared. So that's going to be 1 over x, so plus 1 over x. And then finally, we've got minus 12 over x squared. Okay, and we can't cancel anything in the numerator, so we just leave that as it is. So minus 12 over x squared. Okay. Now, this is f of x, so this is f of x. So what I need to do here is differentiate this one time with respect to x, and then differentiate that result again with respect to x. So f prime of x here. Well, starting with the 1, that's a constant, so we'll differentiate to give us 0. I've got 1 over x now, so what I need to do is I need to get this in the correct form. So if I do it over here, this is the same now. It's a little bit messy, but 1, so that stays as it is. 1 over x, well, that's the same as x to the minus 1. So that's plus x to the minus 1. And I've got minus 12 over x squared, so that's the same as minus 12x to the minus 2. Okay, so these two things here are the same. What I'm going to do is I'm just going to highlight that, just so it's not confusing. So this here on the left-hand side, well, I've got 3 parts. I can't really see the left-hand side, but this here is equal to this. Okay, remember, I'm just writing this in index notation. Okay, so going back to our original pen color here, once I differentiate it, this part here is 0. X to the minus 1, that's going to be minus x, and then we subtract 1 from the power, that's minus x to the minus 2. And I've got minus 12x to the minus 2, so that's going to be positive 24, so plus 24x. And what I do then is subtract 1 from the power, so that's to the minus 3 there. Okay, so that's f prime of x, but what we want here is f prime prime. So we need the next derivative here, the second order derivative, f prime prime of x. So again, just going through now one more time and differentiating with respect to x. So minus 1 times minus 2, so that's positive 2, so we get 2x. Subtract 1 from the power, so that's 2x to the minus 3. And I've now got 24 times minus 3, so that's going to be minus 72, minus 72 there, x. And again, just subtract 1 from the power, so that's to the minus 4 there. Okay, and there we have it, so that's our solution to part B. So 2x to the minus 3, minus 72x to the minus 4 there. Okay, that's our solution. So now let's take a look at questions involving stationary points and determining the nature of that stationary point. So what I've got here is a curve C, which has this equation. So a nice, simple, straightforward quadratic. Now for part A, what we're going to do is verify that C has a stationary point at x equals a half. So the first thing I need to do here for part A is just simply differentiate this. Now when we talk about stationary points, remember straight away we need to be thinking of dy by dx equals 0. Okay, so what I want to do is just differentiate this and set that equal to 0. So differentiating here, so for dy by dx, we go term by term. Well, x squared, that would be 2x. We get 2x there. Minus x, that will give me minus 1. And this plus 8 here, this positive 8, once we differentiate that, well, that will be 0. It's just a constant, okay? So for dy by dx, I get 2x minus 1. Well, we say that a stationary point occurs. So stationary point, that's when dy by dx is equal to 0. Okay, so what I do now is set 2x minus 1 equal to 0. So 2x minus 1 is equal to 0. And now we just solve for x. So 2x is equal to 1. Divide both sides by 2, and we get x equals a half there. Okay, and that verifies that C has a stationary point at x equals a half. Now for part B, it says using differentiation, determine the nature of this stationary point. So we can think about this quadratic here. And we can look at it and we can see straight away that this will be a minimum point, okay? Because this is just a positive quadratic. So it's going to look, say, something like, I don't know, something like that, okay? Just a very quick example. So we know it's going to be a minimum, but we need to use differentiation to show that this will be a minimum. So what I'll do is I'll just clear the screen here. So for part B here, using differentiation, well, we need the second derivative. So dy by dx, going through this again dead quick, that's going to be 2x minus 1. What I need to do now is differentiate again. We need the second derivative to determine the nature of a stationary point. So the second derivative here, all we do here now is just differentiate this one more time. In that case, we're just simply going to get 2. Okay, so we get this is equal to 2. Now here, we evaluate the nature by looking at our second derivative. So we compare this to 0. So is this greater than 0, less than 0, or equal to 0? Well, clearly, from here, we can see that the second derivative is greater than 0. Okay, 2 is greater than 0. So therefore, because this is greater than 0, this shows that we have a minimum stationary point. Okay, this is a minimum as the second derivative. So the second derivative here is greater than 0. Okay, and that's all we simply need to show there. We just need to show that the second derivative, in this case, is greater than 0. Okay, so there we have it. So that's our solution to that question. And let's finish with one more question here. Again, I've got a curve C which has this equation. So we've got y is equal to x times x squared plus x minus 1. Now we think about this, this will actually be a cubic. Okay, if I expand this here, I'm going to get y is equal to x cubed plus x squared and then minus x. Okay, so if I think about sketching this here, again, don't have to be perfect. But this is a positive cubic. It's going to have that end going into a U shape. So it might say, look, something. Let's try that again. That wasn't very good. Let's try one more time. So let's say it's going to look something like that. Okay, we've got this end shape here where I'd say have a maximum stationary point here, and I would have a minimum here. Okay, so we need to be able to deduce now whether this will be a local maximum or a local minimum. Okay, and this is why we need the second derivative. So the first thing I need to do here is differentiate, set this equal to 0. So dy by dx. So we differentiate here term by term, x cubed, that would be 3x squared. X squared now, that would be plus 2x, plus 2x, and then minus x here, this will be minus 1. Okay. Now, when we're looking for stationary points, we set this equal to 0. Okay, so now what we do is we set our quadratic here equal to 0. So 3x squared plus 2x minus 1 is equal to 0 because we set dy by dx equal to 0. Here, what I'm going to simply do now is just put this into my calculator. You can factorize it if you want. but I'm just going to put it into my calculator. So obviously make sure that A is 3, B is 2, and C is -1. And what I get here now is my two solutions as we'd expect. So I get one solution is a third, 1/3, and I also get a solution of x equals -1. Okay. Now clearly looking at this and my diagram here, these two x coordinates aren't correct. Okay, but what we're saying here is that one of these x solutions will be the local maximum, and one of these x solutions will be the local minimum. So what we need to do now is deduce which one corresponds to the local maximum and which one corresponds to the local minimum. So what I need to do now is make use of the second derivative. So let's carry on over here. So the second derivative now, just differentiate here dy by dx one more time with respect to x. 3x squared, that would be positive 6x. We get 6x there. 2x, once I differentiate that with respect to x, that will give me +2. Okay. So that's our second derivative, okay, because this -1 will become 0 once we differentiate it. So to determine the nature now of these stationary points here, what I need to do is substitute each of these into my second derivative. So when x is equal to a third, I do 6 times a third. So let me try it here. It's going to be equal to 6 lots of a third plus 2. So I get 6 times a third, so 6/3, which is 2, plus 2, so I get 4. Okay, so my second derivative is equal to 4, and 4 is greater than 0, so therefore that corresponds to my local minimum. Okay, that's our local minimum. So obviously when I substitute x equals -1 now, what we should get is that this is less than 0. So let's just verify that here. So when x is equal to -1, I get for the second derivative 6 lots of -1 plus 2. Okay, so clearly this is -6 plus 2, giving me -4 there. Okay, and clearly -4 here is less than 0. So therefore, that corresponds to our local maximum. Okay, so that's our maximum. So what we need to do now is work out the coordinates of the curve's local maximum. Well, we know the x coordinate, that's -1. All I need to do now is substitute that back into this equation here for y. So when x is equal to -1, that corresponds to our local maximum, and therefore we can deduce the y coordinate by substituting this back in. I do -1 times -1 squared plus -1, so that's the same as just -1, and then minus another 1 here. Okay, so let's just take care here. I've got -1 on the outside, -1 squared, so that'd be +1, -1, so that'd be 0, and minus another 1 here. Okay, so let's just be very, very careful and make sure I've not made a mistake. So they cancel, I just get left with -1. So -1 times -1 gives me +1. Okay, let's just verify that here. Again, I probably should have just used that. That would have been easier. So -1 cubed, again, let's just do it here. -1 cubed plus -1 squared, add -1. Okay. -1 cubed is -1. -1 squared is +1. And -1 is +1 as well. Okay, so -1 plus 1 is 0, plus 1, I get 1. So yeah, perfect, that works. Okay, so you didn't have to do that. I was just double checking it because there's so many -1s here. But we get +1 there. Okay, and there we have it. So the coordinates, so if I just do it up here, so the coordinates for the local maximum are given as -1, the x coordinate, and +1 for the y coordinate there. Okay, so that's our solution to that question. And there we have it. So that was actually a bit of a longer one than I expected, especially that question. But there we have it. So that brings us to the end of this video. In the next video, what we're going to take a look at now is modelling with the derivative and differentiation.